Okay, we're going to look at a second type of sorting algorithm called the insertion sort algorithm. The insertion sort algorithm sorts a list. It takes by taking the next number in the unsorted portion of the list and inserting it into the right position in the sorted part of the list. We're always going to assume that the first number is in the right spot, and then we'll look at the next number and decide where does it go. Then we'll look at the next number and decide where does it go in the sorted list, and so on. Each time you go through insertion sort, you get one more number in the right position of the sorted list. It may not be the final position. In bubble sort, every pass puts a number in its final position. With insertion sort, we don't know which numbers are in the final position until we've made it all the way through. But each time we get a partially bigger sorted list. So we start with one item sorted, then two, then three, then four, then five. So we just keep introducing the new number and putting it in the right spot until we have no more numbers to consider. Now these are only two of the very common sorting algorithms. There's the selection sort, and there's all sorts of other sorting algorithms that you might learn about in a programming class, but these are sufficient for us for this semester to show us how it goes. Now again, here's some pseudocode from the textbook. We have a for loop for j gets from 2 to n. We always assume that the first number, a sub 1, is in the right spot, and then for every other number, we're going to have to decide where it goes. Now, once you get to a new number that's unsorted, you have to start at the beginning of the sorted portion. That's why I gets 1. J is going to go through the unsorted part of the list. I will go through the sorted part of the list. What we have to do is, once we just trying to figure out where the next one goes, is we work our way through. We keep asking ourselves, are we bigger than the current number? If so, look at the next number. If we're still bigger, keep moving down. So we're going to keep moving down the sorted portion until we find a number that we're no longer bigger than. Right? And once we're no longer bigger than that number, that means that's the spot we belong in. So the way we're going to insert the number into the right spot is we're going to temporarily store a sub j. A sub j is the new number we're trying to put in the right place. We're going to store it in m, and then we're going to slide everybody down. Don't get too hung up in the subscripts and all these calculations here. What this for loop is doing is basically sliding everybody down to the right. So, but it starts at the end so that you don't lose anything along the way. And then once you've moved everybody down to the right, you have an open spot, and you can put m back into its right spot. Again, there's a lot of updates to the variables here, and trying to trace through these with i's and j's as numeric values will be a little bit time-consuming and not necessarily helpful to demonstrate the algorithm. So we're going to use a visual approach, just like we did with bubble sort. Okay? So we're going to sort the same list in the same order that we did in the previous example with bubble sort, but this time we're going to do it using insertion sort. And we have slightly different notation here. What we're going to do is use a vertical line to separate the sorted and the unsorted portion of the list. So we always start off with the first number assuming being sorted. So everything on the left here is sorted, and everything on the right here is unsorted. Okay? So we'll use this vertical line right here to keep these two lists separated. And we're always going to take the number that's just the first one of the unsorted list, just to the right of that dividing line there. Okay. Now, let's go through, now that I sort of introduced the notation, let's do this a little bit more cleanly without all those extra words there. Here's how we're going to trace through this on paper. We're going to start with the number 1. That's the one that's sorted. Right? That needs to be sorted. And we go to the beginning of the list, and we ask ourselves, is 1 greater than 3? 1 is not greater than 3. Right? So that means that the 3 is going to get slid down, and then the 1 is going to end up in its place, right, 1 comma 3. Now we have a sorted list of 2 instead of a sorted list of 1, and we have 3 left unsorted instead of 4 left unsorted. Okay? Now when the 7 gets considered, we ask ourselves, is 7 bigger than 1? Yes. Is 7 bigger than 3? Yes. Is 7 bigger than 7? No, so that's the place that the 7 belongs. Now, again, it would, if we were doing this by hand, we wouldn't pull the 7 out and then put the 7 back in, but that's what the algorithm's going to do. Nobody's going to get slid down. In this case, the 7's going to come out temporarily, then the 7 will go back into the place because nobody gets slid down. So we'll have the numbers 1, 3, 7 now sorted, and 5, 2 left unsorted. Now the thing to keep in mind, in order to show all of the steps of the insertion sort, you really do need to show all the comparisons that happened. As long as A sub j, that's the new unsorted item, is bigger than the current one in the sorted list, you have to do a comparison. So the first time we only had one comparison. Here we had actually 3. We compared 7 to 1, and then we compared 7 to 3, and then we compared 7 to 7. Okay? So let's continue on to the next iteration. Now we're going to consider the number 5. The number 5 is bigger than 1, it's bigger than 3, but it's not bigger than 7. So this is where the 5 will belong. That means that the 7 will have to get moved down, and then we can insert the 5 into the right spot. The only number left to be considered is the number 2. The number 2 is bigger than 1. It's not bigger than 3, so that's where the number 2 will go. So the 7 will get slid down, the 5 will get slid down, and then the 3 will get slid down. And the algorithm is going to do it in that order. We could talk about that in a minute, but that's the way the algorithm is programmed to do it. Then we have finally the sorted list 1, 2, 3, 5, 7. Okay? So this is sufficient as far as a diagram tracing the algorithm. I can see all the comparisons you made. I can see who had to move down. I can make sure that you followed the algorithm and didn't just sort the list itself. Now going back to the issue over here, the idea, the way the algorithm works is the 2 gets temporarily stored, out here somewhere in a variable m. Then you can move the 7 on top of the 2. You can move the 7 on top of the 2 without worrying about erasing it because the 2 is already being stored somewhere. If, on the other hand, you tried moving the 3 onto the 5 first, you would lose the 5 because once you've overwritten it, it's gone. So the reason the algorithm over here, all these indices are a little bit complicated, it's to make sure that we start at the end of the list. That's what the j minus k is. J minus 0 means the jth one, right? And then you just slide everything down but the previous one. Okay? So the 2 gets overwritten by the 7, and the 7 gets overwritten by the 5, and then the 5 gets overwritten by the 3, and that way we don't lose anybody. That's not something you need to worry about right now. You're just going to, I won't be able to tell which order you wrote these arrows in anyway. You're just going to perform the algorithm by showing all the comparisons that are made. Okay? So it's important that you learn how to trace both using bubble sort and insertion sort. And if you learn any other sorting algorithms, you would then worry about those as well.